喂，这边线上听不到声音。
放在耳朵。
对，对，好，然后把它拉下来一点。
还是反过，这样子。
哎，我怎么觉得？
我觉得哪里怪怪的，好像怪怪的。
哎，应该是这样子。
这样子。
哎，是不是？对对对对，这样对，这样子对对对。
这样子。
对，然后这个我调一下，等一下。来回应。
好，这样。
太靠近。
好，没有没有，我再把它11点。
不用这个是。
这样子。
帮忙一下。
对，这样子，我们好像可以，好像有一点微调。哦，是要。应该是对，你看那个是对的。这样子对对的。
对，这样大概是对的。
好，那就，对，就先这样子。所以这样鸡刚听得到吗？
喂，现在可以了。
哦。你们应该是假设应该都会有的吧？
可以。好如果要问问题，记得要拿麦克风，就是作为这个收音的部分。Okay, so welcome everybody. So starting from this semester, we're going to have the so-called preprint seminar, and the purpose of this seminar is try to for people here to present the most recent work. The most recent work means that in recent 2 years. So all the presentation will be based on the preprint in this recent 2 years. And so our first speaker today is Dr. Chen Yan'an, and he's going to talk about infinitesimal structures of local clinical thresholds by Liu Jihao, Meng Fanjun, and Xie Lingyao. Okay, yeah, so please start.
Okay, thank you. Yeah, so I want to talk about this. Let me say, let's study something called infinitesimal structure of local number thresholds. So, in the first half of this talk, I would like to motivate you why we want to study local number threshold. So I think the story comes from we want to classify in variety. So we will want to so what is so-called minimal model program. So what minimal model program does is starting from some variety, and let's assume with some mild singularities. So we want to find something called minimal model in the birational class of X. So here, what we mean is that, Okay, let me probably write a definition here. So we say X is minimal if the canonical divisor is nav. So in other words, so the intersection number with each irreducible curve is non-negative. Okay. So how to do that? So first, this is communal model program. So the starting point is we will input called X. So we will want to ask. So we ask, is this KX is nav? So if it's yes, then it's minimal. So that is something we want. But if it's not, then we need to do something. So what we want to do is, you see, we want to achieve this property. So we want to have naveness. In other words, I mean, if this is not nav, that means there's some curve such that this intersection number is negative. So if we want to make this nav, that means you want to contract down this curve. So this here we will need a very important theorem. So it's called cone theory. So what cone theory says that roughly speaking, so let me see how. Okay, I won't write down every detail in the cone theorem, so I just write down what I want. So right here. So for kx negative extremal ray, let's say R. So what we want to do is we want to study this N1, I mean something Mori cone inside this. So this is actually a finite dimensional vector space. We want to study this cone, and so if we find if there's a negative kx negative curve, then we could find something called kf negative extremal ray for this cone. So here, extremal just means that it should be lie on the very outer part. That means, okay, let's just write. So that means for each R1, if R1 plus R2 inside R, that means R1 and so that means extremal ray. Okay, so for such extremal ray, we could show that there's a we call contraction associated with this R. So from X to, let's say, Z. Okay, such that, so this is a contraction and no, what I want. This is not what I want. I want C. Yes. Okay. So that means we want to, so there is this contraction such that if we contract down all the curve in this ray, and this is very strong. So we only contract these. We won't contract others. Okay. So now, so then we will divide it into several cases. So the first case is if the dimension z is less than dimension x. So in this case, we call this pi r is a Mori fiber space. Okay, let me just run Mori fiber space. And we will feel this is a positive outcome for the middle model program. Okay. So then the program will stop here. The second will a case when dimension z is equal to dimension x, but consider the exceptional set for this pi r. If this exceptional set is a divisor, that means the codimension is 1. Then we call this is a divisorial contraction, and if we are in this case, then actually it's very good. That means we just need to replace x by z, and then we will start again to check this z, if this z is nav, and go this process again. So okay, so the third one will be for the dimension z is equal to dimension x, and now the codimension for the exceptional set is at least 2. Then we call this is a small contraction. So for this, in this case, the problem is that the singularity for z is too singular. So actually, you could show that it's not hard to show that z is not, I think it's not Q Cartier. I mean KZ. So it's not good. I mean, yeah, if it's not Q Cartier, somehow something we could not study what's nav there. Yeah, if we want to, you need to have these to be Cartier so that you could consider wise intersection. So that's some difficulty here, but Mori gave a brilliant solution, or yeah. So he proposed that we could consider a flip. So that is, we will draw something like this way. Okay. Okay. So this is called flip. I just skipped all the definition for flip, but the idea is that here we contract down some curve that is intersect kx negatively, but flip will make this curve to be something intersect kx dagger positively. Okay, then if we are in this case, we will replace x by this x dagger and then go to x, kx is nav again. So the problem is if this program will terminate. So you see, if we are always in the second case, I mean, if in the second case, the good news is that we contract down the divisor, so the Beatty number is decreased by 1, and we know the Beatty number is finite, so we won't always in this case, or if you always in this case, and this program will stop here, or not here, somewhere there. So the problem is here, the Beatty number for these two guys are the same, so there's no easy reason why this this program will stop somewhere. So okay, okay, let me see. Actually, I also cheat a little bit. So I mean, at the time when the Mori proposed this, we don't know the existence of leads in general. So, so for this solution, there are two main issue need to fix. So one is the existence of leaves, and another one is why I just mentioned the termination of leaves. And actually, this is have been proved by, I think by BCHM. Okay, let's just write this. Okay. So now people want to figure out the termination of leaves. Okay, so now the next, there are some people propose how to study this termination of leaves. So one way to study is by, I think it's proposed by Shakurov. So Shakurov says that if assuming something I will call ACC for MLD, and LSC, assuming two conjecture on something which I will define later, then so there's no infinite sequence of blips. Okay, so now, so in other words, we kind of reduce the question to another question, two questions to study the minimal log discrepancies. Okay, so, well, so it's time to define what is minimal log discrepancy. Yeah, so I will define this there, and then I will talk about what is local non-closed ratio. Okay, let's define what is. So now what we are starting from a pair. So a pair. So it's a variety with some, and B is just some divisor. And we need to impose kx plus B is, I think, is at least, let's assume Q Cartier. So for any exceptional divisor over X, so okay, let's do in this. So for any birational map, Morphison, and E a divisor on Y, we could first do this. So we always have this one. Okay, we also always have this divisor by. So we could define the low discrepancy. So we could write A of E x B. This is just nothing but the, okay, for this, so I won't, if there's no one here, then this is discrepancy, but since we are doing for, it's more convenient to do a low discrepancy here. So I put one there. Okay, so this is low discrepancy. Then okay, so this is so how that means if you write out these, the easy way is if we write out this by as a sum of the then this number, or I think I should say these di are all distinct. Then this one is just some AI for yeah, for this D I is just, and if there's no such DI, then we will divide this to be 0. Okay. Okay, so next one should be the, so we could define the set of, okay, now, I mean, we could define this minimal low discrepancy for the pair XB. So this will be the increment for all such number. Okay, and let me put more definition. So there will be, so this is called total minimal low discrepancy. So so this is just we allow the divisor is not exceptional, that means you need to put you need to consider also the irreducible component for this B. Okay, so then we could easier to define. We say this pair is log canonical, if so we define the pair what is the log canonical, then we could define what is log canonical threshold. So we define the log canonical threshold for the pair respect to, I write D. This will to be the suit. Okay, so we define what is the log canonical threshold here. Okay, maybe I should go back to here. So what is here ACC for MOD here means? It means that if you put all the search number MOD together into a set, and if you fix a dimension and also fix something, all this number will form a called ACC set, which means that any sequence increase any non-decreasing sequence. So we say S is an ACC set, means that for any non-decreasing sequence, this is decreasing sequence in S, and AI is non-decreasing. Then, and actually it will be stable. So that means then there is this some capital N such that AI will equal to AN for all I greater than N. Okay. Okay, this is called ACC set. And another conjecture, okay, maybe mentioned. So ACC for MOD, now we only know, this is now only know for the up to dimension 2, up to surfaces case. We still don't know, yeah, it's still wide open for the threefold. And another conjecture for MOD is, this is called lower semi-continuous. So this consider, so this just, we consider a function A from the set of point. This is just, we put any point X. This is, we consider the minimal low discrepancy. At least it's close point. And this just means that the exceptional divisor, the center for this exceptional divisor is this point. And this conjecture states that this function is lower semi-continuous. And this is known up to dimension 3. And also, and both are known for the toric case. for all dimension. So in this paper, they want to study some structure on low canonical thresholds. So why we want to study this, not just MLD. So well, one reason is that low canonical threshold is easier to study. So it's low canonical. So that means somehow we could do a junction, so we could reduce the dimension, so it will be easier to do it. And another,
Yeah, and so when we define the low canonical threshold, then we need to determine whether it's low canonical or not. And to determine it's low canonical or not, then we need to compare all discrepancies.
yes.
So in some sense, how do you see that it's easier to determine than no discrepancy?
Well, it's still very hard, but I mean, um, what I mean is that if this C is actually a low canonical threshold for the then you could actually that means there is this some exception divisor, they say on Y, and they say this map is, and such that we could write this KY plus E plus, okay, let me write DY. Yeah, since this is low canonical threshold, so we actually have something. This is the coefficient should be 1. Easy to see. Why erase? Okay, I erased that. But when I define the low discrepancy, I mean this should be defined to be 1 minus the multiplicity. So the low canonical threshold, so it's a soup for this condition. That means there is something such that the low discrepancy should be 0. But low discrepancy to be 0, that means the multiplicity should be 1. And if we have this one, and we could do a junction, so we reduce to the lower dimensional case, then hopefully it will be easier. Oh, 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 yeah, so that's my bad. Yeah, so I should write this should be B plus CT. Yeah, yeah, thank you. Yeah. Okay. Okay, another fact is that I think it's by, okay, another fact. So this is the ACC for MLD will imply the ACC for LCT. For the same dimension. And this is proved by first by Bilka and Shakurov, assuming the BAB conjecture, and then BAB conjecture proved by. Okay. So actually, so people will somehow study both. So okay, so I want to mention there are some results on the ACC for LCT. So this is proved by the so LCT holds 4 dimension. So this is by Hacker, McKernan, and Xu. Okay. Okay, so now this is all the story. Any questions? So now, so this paper just want to study more. I mean, now we know this is ACC. They propose some property. They will show the set for local Canal threshold is standardized. That's what they call them. And it's kind of it gives us more information for this set. So let's give a definition. We put put it here. I think maybe some issues. Let's see. For if you consider just a one-dimensional case, just let's put some C is a curve. Okay, let's make it easier, smooth curve. And we consider the divisor. Okay, I think we should put it a pair. So we consider C a pair. So the low canal threshold for this guy, okay, no boundary with respect to some divisor. So it's just some point. So this will just mean that the soup for such that the C D is low canonical. Okay, so but actually, for the curve case, if we impose a low canonical, what we mean is that you want this how do I write? You want all the coefficient for this guy to be at most 1. Right, this is just because this is low canonical, so the condition will be 1 minus multiplicity of some point. This should be, so that means so in this case, if you consider this D is just is reduced, or oh well yeah, I think yeah, there will is it yeah yeah yeah, I think yes. Yes. Um, somehow something I forgot is like I think is there we have something if on C2 we consider as a region, and if you consider this divisor. mm, Yeah, so this is the cusp. Okay, yeah, I think is it something like this one? Okay, this is the cusp. Is it? Uh, I think it should be this one is better, right? Yeah. So you consider this one. Uh, yeah, you could do all the calculation. I mean, you need to resolve. Yeah, we know from I think in Colombo's book, if you want to compute some, let's say, let me just write in this way. If you want to make sure this the low discrepancy for this guy, you need to resolve to find is up to some model such that everything should be simple normal crossing. So you just try to resolve this guy, and I think you need 3 blow up, I think, and calculate all its discrepancy or low discrepancy. And I think I remember the answer will be 5, 6. I mean for the low canal threshold. Yeah, I think I remember. Yeah, yeah, just some. You just need to do blow up and very careful to compute all the discrepancy, and you could see this. So well, so this is one case. So this number will in the set of all the low canal threshold. Okay. So any other questions? Uh, low canal threshold. I forgot it. I think it's okay. Let me. Yeah, I mean the formula is not on the top of my head. So I think is it? You mean this one? I think. Uh, do we have? Yeah. Okay. 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 So yeah, this is. I think. And if you consider low threshold. Let's see. Yeah. Yeah, this is also another something we could compute. Yeah. Okay, thank you. So if you consider like I don't. Okay, that is another example. So yeah, I think in general it's pretty hard to calculate this local number threshold as well as the minimal log discrepancy. Okay, so let me give you the definition for the what they call standardized sets. So oh yeah, that's a key point. Yeah. So this is a okay. Yes.
What is the sequence? How is the sequence defined in your ACC set? Like, it's supposed to be like what will the sequence be like? Or is it that?
Or like, okay, let's try to write down something like, let's say n is 2, that will be easier. So maybe we have let's try to find something bigger.
I think I get the idea.
Yeah, something like this. And you could find something another bigger.
Yeah, okay.
Yeah, so you see, yeah. So it's not hard to show. Yeah, it's an ACC set. Yes.
Okay. Thank you.
Yeah. Okay. Oh, hold on. So we if we fix a gamma is a subset of R real number, and the gamma is so we say this gamma is a stand is near this gamma. I think they put gamma nodes. Okay, let's use it. If there is this m epsilon positive real numbers and m positive integers and some b1 to bm, some real numbers such that this gamma intersects gamma 0 in this, so it's nearby. This will into So this image. I think we should union gamma. So what you mean that the standardized just means that locally near this number, it will look like this way. So it's like what we like to say is a standard set. Yes, yes, that is how they set up the definition in the paper. Yes. So so in their paper, the standard set is neither ACC nor DCC. It depends on how you choose this PI. Okay. Okay, now we want to study. So you see, if they said if gamma 0 is not an accumulation point, then okay, I should emphasize when I say accumulation point, that means we actually do have an infinite sequence and tends to approach to this number. If it's just if this sequence is just a kind of finite sequence, I mean, then yeah. So we need to actually have an infinite sequence to approach this gamma 0, to approach some number, then we call this number is an accumulation point. So to see, I mean, if this gamma 0 is not an accumulation point, then this is, I mean, this condition is free. You just pick I mean, near this gamma 0, it just decrease, so you just pick a very small epsilon. So if we want to study this property actually impose some condition on the accumulation point. So we will use this notation, the partial gamma. This is the set of accumulation point. So and also we have the notation partial K gamma. This just means that we tell K minus 1 this set, the accumulation point for this set. Okay. Okay, so we will also have some following definition. So we say this gamma is, they call, yeah, it's just their terminology, weakly standardized. Now we saw this is for global, it's not near something. So we say this is weakly standardized, means that gamma is, okay, standardized near gamma 0 for all the accumulation point. So actually, the weakly standardized impose the condition on the first accumulation point, but not the higher accumulation points. And the reason is easy. It means it's just by our definition. I mean, if this gamma 0, this gamma naught is impossible it's impossible to be a second in a second accumulation point. Just because we say if this is standardized, it means it needs to inside this set. But if the accumulation point for this set is just gamma naught, so the second accumulation point is nothing. So we cannot impose a condition on the second accumulation point. And they say gamma is standardized. If all the partial, this is weakly standardized for L. And there is this is empty. Okay. So this is the definition. Okay, so yeah, it is standard. It's standardized. So maybe let's oh, okay. Let's do for this guy. So that's us. This is n. So let's put Sn or gamma n or Xn. I think so maybe let's do for S1. So if you just have no summation, one thing. So this is easy to see for this guy. This is just 0. And so you just need to check. Okay, so we don't need to check the second one. So this is empty. So we need to only check around 0. But around 0 is just 0 plus 1 over n. So you just pick okay, here. Yeah. M is 1 and also only one real number is enough. Okay. Then let's see, consider this one. So this is okay. Now this should be S1, right? Do you believe it? Or maybe, yeah, you are right. Yeah, but okay. Yes. Yeah. Thank you. Yeah. So and you could do the second one. So second one, S1. So second one should be 0. So now you see if we check the first accumulation point, there is something, okay, 1 over n. So you see around 1 over n, you just again pick the BI, it's just 1. And then that's it. And that's why and the reason I want to put it here is here. The second accumulation point is 0. Around 0, you don't have any possibility. You cannot, it's impossible to have this condition, right? If you want to put this, you need to have infinitely many BI, but it's not allowed. So around 0, this is not standardized, but it's okay. For the gamma to be weakly standardized, we only impose the condition on first accumulating point, but not on the higher one. So yeah, you could do this. So I think, yeah, so for Sn, you could see the first occupation point should be Sn minus, yeah, I think so. Okay, yeah, you could check it. I think I think so. I think should be this one. Okay. So such set is not only an ACC set, but also a standardized set in their definition. It's not so. Yeah. Yeah, that's a key point. Yeah. So you need to exclude the second accumulation point. Yeah, I think what's the issue is so you cannot do the I forgot the number, but I think the issue is this one. So we not consider if the number is second accumulation point, we don't impose any condition. Yeah. Okay. Okay. So then what should I do? So I think the main theory in their preprint is that the set of LCT, if you fix the dimension D, and let me just put it. I should write more. Okay, what that means that this is the set of LCT and X. Okay, I think this is empty. Okay, no. They put this is reducing. This is reduced. Okay. This has only coefficient 1, and you put such that. Okay, let me put the gamma here. So the coefficient for this D will inside this gamma. Okay, I should write dimension. It's D. And here this B is only they only allow it to be reduced. So they want to say, okay, this set is standardized, but we need to impose some condition on this gamma. So, okay, so they will say, the condition, okay, the condition is the condition is we need to, this gamma should be also standardized. The first accumulation point is 1. And also 1 need to inside this gamma. I think that's almost, there's another technical, and also the gamma should be equal to gamma plus. This is just finite sum of gamma intersects 0 and 1. Okay, actually, except for this standardized, I mean, if you replace this standardized, okay, I think they, if you just say, okay, this gamma is a DCC set, and we have the one is only the accumulation point, and we have this one, then actually in Hecker-McKernan-Schul's paper, they show that the accumulation point for this guy is just the D minus 1. I think I forgot. I think we need to include 0 or 1. Okay, let's put, I think it's 0. Okay, I think let's put it, I think maybe there's some typo, but I think what they want is this must be DCC set. I think it's okay to write. You have standard set, you only accumulation point only 1, and okay, and this is inside 0 and 1. I think it's okay. Okay. Standard set is LCT. So you mean the standard set should be, you mean all the standardized sets? I think it's not easy to see, right? Or you maybe try the curve case. Yeah, and I think it could be done. Yeah, I believe. Yeah. Okay. Okay, so I won't show the proof on the board. It's very technical. But actually they follow the proof. They follow the proof in Hecker-McKernan-Schul. So maybe let me write down more. Oh, yeah, there's some example we should write down. Some counter example. So it seems that whenever I say ACC set is a standardized set, but we should give a something. This is not true in general. So we consider the set of n plus this one. So you see this set is an ACC set. You should check it. And the only accumulation point is 0. And so if we want, and it is not standardized near 0, it's not possible. Yeah, you could check. So roughly speaking, so they in their paper kind of propose, okay, all these ACC say seems to have the standardized. They will like near the accumulation point. They must be like in the standardized way, not like this one. Then they propose. They give a also not some other examples. So let me just write it down. I think we don't have too much time to cover it. So for MLD, like the degree is 1, if you put the so to make our life easier, let's just put this gamma is a finite set. So this is it to see this one? So this is standardized. I think it should be M. Write it down something. Yes. So okay, I just assume this is finite. So this is also finite. So this is standardized. So this is not interesting. So also we could show that the minimal low discrepancy for surfaces. So no, I don't have. We cannot write this down, but this is also standardized. Standardized. Okay. The proof for this is the proof for this is should be go back to the proof by elastic. I mean, the MLD on surfaces satisfy ACC is proved by elastic, and we need to use his proof to show this standardized. So okay, maybe let's. I want to. Okay, I want to say some. I think the key observation is, I mean, they find maybe an easier way or a way to show the standardized. So let's take this for example. So how to show this standardized? So actually, we need to first take a sequence. They take take a sequence inside this. Okay, just we take a sequence, and by some argument in elastic work, we could and by passing to a subsequence. So we may assume AI is roughly like this way. Okay, let me alpha delta is positive. And this delta is a rational number, and this AI is a positive integer. And all these are constant. That is a constant. Oh, yeah, there's only, index is only this one. Okay, so you, what I mean is, so if you start from a, we observe that if you start from a sequence, then we could pass into a subsequence. We may assume we have this one, and you see this limit is actually alpha. Okay, let's write A0. So you may write this Li to be A naught plus something, and you could do this work. I just write all the results. So you see this is a constant, and this is just some, oh, you need to do something. This is rational number. So, and this is just a positive integer. So you just kind of, you could make this part, make this one to be inside some something that, oh no, this one. So what we did is that starting from a sequence, we could always pass into a subsequence such that is like they still call it a standardized way. Okay, so they showed the lemma. So they say if any set, for any set, if we could find this property, that is, for any sequence inside this set, you could always find a subsequence such that it can approach to this limit in a standardized way. Then they show that this set is standardized. Let me put S. So then, so that means if for all sequence inside this S, if for all sequence there is a subsequence such that this approach to this limit in a standardized way, then the set, this is also standardized. We don't have let me try to finish this lemma. I think this is kind of not hard to do this lemma, but this, so you see, they made our life easier. You just need to check this one. So the way, so I will assume, so first thing is the proof. You could always assume, we must assume this A0, you just add minus A0 for every element. So you could assume this A0 is 0. And also, I mean, just, yeah, some move by some translation, and also okay, here there's a technical one. So now they define an equivalence relation. So two numbers are equivalent if they are differed by the rational number. So now they would like to study. So that is something we want to study. So this is anyway. This is not the notation is not important. They study this set. They consider all the as I write as so. Remember, we have already moved this to the center. So so just this one. So the important thing is that this set must be the finite set. So I think okay, I just say out loud. So if it's not a finite set, so you could find a sequence, and all the and each element in this sequence have a different, distinct equivalent class. But our assumption says that passing to a subsequence, they must approach to a standardized way. That means after passing to a subsequence, those AI should be inside to something like this one. But this is a finite set. I mean, finite, the equivalent class is finite, only have finitely many equivalent classes. So this is but this, by assumption, this is infinite, many equivalent classes. So this is not possible. So this must be a finite set. So if it's a finite set, so that means we only have finite many equivalent class. So you could write down this is just some finite. Let's write K. Okay, there's a finite union, and there's each one is just we have one. Let me make sure I could write down correctly. So it's just some C. Let me just write this is just inside Q. So you using this equivalent class. So you just separate them. So each gamma K is just kind of represents one equivalent class. So this is one number, and all other it just differ by a rational number. So I should, this is not in this. Actually, we know it's inside some gamma primes. So now to make sure this is standardized, actually we just need to study each one is standardized. So we reduce to only one single set like this way. But now for each one, you could just do a dilation. So I mean, you could assume this is one. So now we may assume our gamma K is just some gamma prime and all other rational numbers. Okay, now, so the next part is we need to show this is standardized near zero, and the proof is by contradiction. So if it is not, then that means we could find some rational numbers and something like this one. And because we cannot find it in a standardized way, so that means the numerator should be approach to infinity. But the limit bi is 0. And I think it's not hard to see that this sequence has no subsequence such that the approach to 0 in a standardized way. So it contradicts our assumption. So that means it is actually standardized near 0. Okay. Okay, I think that's all I want to say. I stop here. Like, do I erase? Oh, so sad. I erased it. I mean, like if we want to, do you remember? When I prove this one, the way I do it is I give you a sequence inside this set, and I say I could pass to a subsequence such that you approach to the limit in a standardized way. But this doesn't. So then we need to use this lemma to say, okay, is indeed this set is indeed a standardized set. But yeah, right. It's almost, yeah. I mean, what we just say, the argument I gave before is just tell you that, okay, all the sequence, if any sequence, you will pass to a subsequence, this is a standardized. But you pass to a subsequence. Yeah, but this, but if every sequence you pass to a subsequence, then you could show a standardized way. Then this lemma could show, okay, it is actually standardized. But we do, you see, we do a lot of reduction. Yeah. And I think and this is actually not constructive. I mean, like when we show this is finite, we prove it by contradiction, so we still don't know what's inside this one. We only know it's finite. Yeah. So it's not constructive, but we could show it's standardized, yes.
What does it mean by a sequence converging in a standardized way?
Okay. That means, well, I think this should be, so that means all the AI could be written as A0 plus some N. Okay, let's put it more in general. For some N is positive integer and Bj is just some real number, positive real number. And there are only finitely many possibilities here. Yes.
Sorry, it's the end of today.
Yes.
Oh, I can't hear any voice except the speaker. Sorry.
Oh, so do you have any questions?
I have no question today.
Okay, yeah. So thank you, and see you next time.
Okay.